Okay, so here, so I want to start off by kind of wrapping up from the previous, excuse me, from the previous video. So we left off on the degrees of what I meant to be. We defined the degrees of a vertex in a graph, right? And in general, any graph, whether it is complete or not, in any graph, the sum of the degrees of vertices is always, right, always twice the number of edges. Okay. All right. And again, the reason being is because each edge connects two vertices, right? So if we just focus on the incidence between one vertex and an edge, well, there's a connection on the other end. Hence, they're always double counted there. Okay. All right. So another thing that we're interested in is when dealing with graphs is kind of if we think of them as visiting each node, right? Or not necessarily each node, I'm sorry, getting from one node to another. And the different possible ways that we can do that, right? And how do we call them, right? So we're going to go through the different types of definitions here. So it's best kind of illustrated with an example here. So let's say here we had SB2, V0, V1, and then this is V3. All right. All right, so a walk is just the very most basic general way to call this, or most inclusive one, is simply a walk, right? And we can think of a walk as a sequence of vertices where the adjacent vertices, where right, clear, where the sequence of vertices where adjacent vertices in our sequence are adjacent in the graph. All right. So very generally, like we could say V0, V1, V3. Right now, each one of those are connected, are adjacent. Right. Again, I also got to be very careful with the vocabulary I use. Since, we have a very specific vocabulary here for our graphs, right? So V0, V1, V3, right? Each vertex, right, is adjacent to the one after it and the one before it, right? So that makes a walk. That's it, right? Very plainly, right? Now, from there, you can think of that as a kind of our mother set, the overall set here. And then from there, we can provide more restrictions, right? So if that's a walk, a path is where we have no repeated vertices. Same as a walk, but there's no repeated vertices. All right, so V0, V1, V3 is a path, right? But let's say another, we can go from V0 to V1 to V0 to V2, right? So that's not a path, that's a walk, right? So here, path and the walk. And then this is only a walk. Okay. All right, and from there we can keep going further. Well, what if we define a circuit? All right, sometimes called a cycle. And here we just end end at our initial we end at our initial vertex, right? So here looking at the graph we have up here, right? Again, that's the only condition, right? So we can go V0, V2, V1, V3, V1, V0, right? And that would be a cycle. So here we may repeat edges. Right now, a simple cycle, simple circuit, and there are, so same idea where we end at the initial vertex. But here we have no repeated edges. Right? So for the graph we have up here, then here if we start at V0, we go V0, V2, V1, V0. Right? Simple circuit. Now notice that's not always possible, right? Because if we start at V3, there's no way to get back there without repeating an edge. All right? Okay. All right, and again, we'll get more in detail in later sections in terms of, these circuit cycles. When do I know an existence of them? How to find them, etc. Those are different types of problems, but here we're just defining these, right, as a cycle and a simple cycle. Okay, now one last definition here before we wrap up on the definitions here is this idea of something called a bipartite graph. All right, so looking here at our textbook. Okay, so we say a graph is bipartite if the vertices can be divided into two sets, A and B, with no two vertices in A adjacent and no two vertices in B adjacent. The vertices in A can be adjacent to some or all of the vertices in B. If each vertex in A is adjacent to all vertices in B, then the graph is a complete bipartite graph. And excuse me, and gets a special name, KMN, right? Where the size of A is equal to M, and then the size of B is equal to N. Okay. All right, so let's take a look here. All right. So let's illustrate this with an example here. So let's say we had a graph where I have vertices 1, 2, vertices A, B, C. Let's say the graph looks like this. All right, and here we can see this is an example of a bipartite graph. Right, since we can define two sets, A to be the set 1, 2, B to be the set A, B, C. All right, and in A, right, 1 and 2 are not adjacent. In B, A, B, and C, they're not adjacent. Okay, so that makes it bipartite. Now, it is not a complete bipartite graph, right? Now that would look more like this, right? So let's look at, again, we can add edges to make a graph complete. So we'll do that here, right? So let's say A, B, C, right? So we'll start off with same graph as above, with set A to consist of 1, 2 vertices, and set B to consist of A, B, C vertices. All right. And from here we could see, all right, again, bipartite, but not complete, right? What makes this complete here is if every vertex in set A goes to every vertex in set B. So what I would do here is I would add this edge, and then I would add this edge. Now we have a complete bipartite graph. Okay. All right. Okay, so these are examples of some definitions and an example of a bipartite graph. And here, going back to our textbook here, some of these graphs we refer to over and over. They're special type graphs, right? Especially the complete ones, right? Since, right, they're all, every graph with n vertices has the same complete graph, right? So we have the names for them, Kn, and then complete bipartite, Km and n, right? Which gives us the size of them, right? How many vertices each set contains for it to be complete bipartite. Right, Cn, the cycle on n vertices, so just one big loop across n vertices, and then the path of n plus 1 vertices. Right, and here when they say path, they mean like a simple path. Right, so you don't repeat any vertex. Okay, all right.